Let's take a moment now to try solving one of the problems in the back of Chapter 1. The problem that I've selected here is problem 119, and we're given a number of parameters. We're given the mass of the Earth, the mass of the Moon, and the distance between the centers of the Earth and the Moon. We're also given that we're going to have a spacecraft that is positioned directly between the Earth and the Moon. So if we drew a line between the centers of the Earth and the Moon, we're going to position the spacecraft somewhere along that line. And we're specifically requested to find the distances the spacecraft must be from the Earth and Moon for the gravitational force of the Earth on the spacecraft to be the same as the gravitational force of the Moon on the spacecraft. So take a moment now and pause this video and try this problem yourself and return when you're ready to see a solution. Okay, so let's take a look at what would be involved in solving this problem. We want the force of attraction between the Earth and the spacecraft to be the same as the force of attraction between the Moon and the spacecraft. And so we could write that as this. This is the force between the Earth and the spacecraft, where I've let r be the distance between the Earth and the spacecraft. And that has to equal the force exerted by the Moon on the spacecraft, which I could represent this way. And now the distance between the Moon and the spacecraft is going to be the difference between the Earth-Moon distance and the Earth satellite distance. So that's the distance between the Moon and the spacecraft. So in this case, a number of things cancel out. And so we'll get rid of the g. That doesn't show up past this point. And we'll get rid of the mass of the spacecraft. That's common to both sides. And then what we'll do is we'll cross multiply this expression and rearrange it a little bit so we can see what we're trying to solve for. So I'm going to multiply through by the denominators and further divide by the mass of the Earth on both sides. So I end up with, on the left, I have the Earth-Moon distance minus the distance we're seeking, quantity squared. And on the right, I have this ratio of Moon mass to Earth mass times r squared. If I then expand the left-hand side, I have this. And one of the things you should be able to see is that you're now going to get a quadratic equation in the distance we're seeking, r squared. So we will have two solutions, and we can talk about the relevance of each of those solutions after we take a look at the numbers. So I'll bring the r squared term on the right over to the left-hand side and rearrange this and write it as r squared 1 minus this ratio minus 2r times the Earth-Moon separation distance plus that same Earth-Moon separation distance squared equals 0. And so now, just as a reminder, we know how to find solutions to this using the quadratic equation. And some of you may remember this and some of you may not remember it. I'm going to tell you that we expect you to be able to solve problems like this if I have a quadratic equation that has this form. Then the solution is r is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. We expect you to know that and use it throughout the semester as circumstances arise. So in this case, our expressions for r will look like minus b, which is 2 times this Earth-Moon separation distance plus or minus the square root of b squared minus 4ac, and a is 1 minus this ratio, and c is this distance squared. Okay, so that's our result. And now we can simplify that because this term is going to end up canceling out this term. Under the square root time, we're just going to have a 4 times this mass ratio times the distance squared, and we can then pull that out and end up with an expression that looks like this. So we'll end up with the separation distance times 1 plus or minus the square root of this mass ratio that's going to be the values of the separation distance that correspond to these gravitational attractions between these two bodies being equal. Now, if we take the ratio of the masses, this turns out to be a pretty small number. It's a little over 1.2%. And so if we plug that ratio in, we end up with R being equal to two values. We end up with R equal to either 0.9 times the separation distance or 1.125 times the separation distance. Both of those answers give us a force of mutual attraction that satisfies our equation. If we are keeping to the requirement that the spacecraft actually be between the Earth and the Moon, then the first value is the only one that satisfies that requirement. So we have that the Earth-Moon separation is 38 times 10 to the 7th kilometers, and so we end up with R being equal to, this is the Earth satellite separation distance, 34.2 times 10 to the 7th kilometers, and the value of the satellite-moon separation then ends up being equal to 3.8 times 10 to the 7th kilometers.